So hello and welcome to this session on insights into explainable AI. My name is Aakash. I am the CEO and lead instructor at Jovian. With that, let's begin. So the first question you might have is, what is explainable AI? Well, we're going to answer that, and we're going to look at why it is important, and we're going to look at some ways in which you can use explainable AI. So we'll start by what and why of explainable AI. Then we'll talk about the different types of explainable AI that you have. Then we look at some case studies, three specifically: Lime, SHAP, and PDP. And then we are going to also talk about how you can learn more, because this is a emerging and vast area of research. So I'm going to point to some beginner friendly tutorials that you can start following and applying to your AI models immediately. So first, what is explainable AI and why is it important? And explainable AI is also sometimes referred to as XAI. So if you see the term XAI, you know that it basically refers to explainable AI. Now, let's say you have a machine learning model and you're using it to make predictions. Maybe it is for predicting whether or not you should accept an insurance application. Maybe it is for predicting whether somebody is going to click on an ad. Maybe it is for predicting if somebody is going to potentially suffer from a heart stroke in the next 10 years. So AI is used for all kinds of simple use cases as well as some fairly advanced ones. And you might want to know why the AI model has given a specific result. But if you ask the AI model directly, it simply gives you a result but doesn't exactly explain why. Some do, but most models don't, especially some of the larger deep learning, computer vision, and natural language processing models that we are building these days. So explainable AI is the process of taking the AI model that you've created, and often this model is created by first capturing some data and then training that data using some form of a machine learning model, let's say deep learning, linear regression, random forest, etc. And then applying some interpretability methods so that we can not only get some predictions from a model, but we can actually understand why the model gave a particular result. And there are various approaches into understanding why the model gave a particular result, and we are going to look at a few approaches today, briefly at a high level. Now, why is explainable AI important? Well, the first reason is simply because you want to understand the model's behavior. As humans, we have this innate curiosity of not being able to trust something unless we know how it works. So we want the models that we build to be predictable in at least some form, and we want to understand why they're giving the results that they're giving. And if you're going out as a data scientist and offering a model to other stakeholders, the first question you're going to get is why it returns a particular result. So you better have an answer about it. You cannot say, okay, that is how machine learning models work. Okay, so that is the basic reason why we want explainable AI. But then a second more important reason is because often the data sets that we are working with can contain some bias. So data sets can contain bias, and that can cause a problem. So it's important for you to identify bias within the model by looking at whether a particular feature like race or gender is causing the model to give a particular result. And if it is, then is that biased in some fashion? Do you need to debias the data set? Another thing that you may need to look at is whether there is some leakage within the data. So often when you have a data set, you might find that there is some hidden correlation between a specific feature and the target variable. And this hidden correlation doesn't exist in the real world. It exists maybe just because of how this particular data set was corrected. All right. So in that case, the data leakage may cause your model to give a good result when you're training it, but in the real world, it may give wrong or maybe even harmful results. And for you to be able to find that out, you need to look into the model in terms of how it is actually coming up with a prediction. Okay, so overcoming data leakage is an important reason as well. The third is regulatory reasons. In many areas, for example, healthcare, finance, insurance, you have to provide reasons for why you are coming up with a particular business decision. So if your insurance application is rejected, then the company is bound to give you a reason for why your insurance application was rejected. Nowadays, you're starting to see this in advertisements as well. If you see a particular advertisement, you can now click on it to identify why a particular advertisement was shown to you. And that is where you again need explainable AI to demystify why a certain prediction is being given. Next, you also want explainable AI simply to improve black box models, because we are building these large, deep neural networks and we are spending so much money, so much compute, training these models, putting in so much data. Sometimes you may not understand why a model is not doing better. You've tried everything, you've tuned or hyperparameters, you have come up with all kinds of techniques to regularize the model, but it is still not giving you a good result, and it takes a very long time to train. So understanding which features are having an impact on the outcome without necessarily looking at the model internals itself, that could be a useful way to understand. Maybe you need to change something about the features. That could give you ideas for feature engineering, how to combine features, how to get new features, and things like that. So all of these are reasons why explainable AI is important. Okay, so I hope you're convinced at this point that you do need to have explainable AI. So with that, let us understand the different types of explainable AI. So there are two types of explainable AI. One is model based. So model based explainable AI techniques depend on the structure of the model itself. So for somewhat simpler models like linear regression, logistic regression, decision trees, you can use the structure of the model itself to understand why the model gave a particular result. They are interpretable by design. But in many cases, models are not interpretable by design. So then the other form of explainable AI, which is what is gaining popularity nowadays, which is where most of the research is happening, is post hoc explainable AI or model interpretability. So you've trained a model, you have obtained some results on a test data set. So you have input data, you have predictions, and you have the targets. And now you want to identify why a model is giving a particular result. And again, within post hoc explainable AI techniques, we have a couple of ways. One is a black box technique. The black box technique does not look at the model in any way whatsoever. It simply looks at the inputs, it looks at the predictions, and then you do something with them to figure out which features have impact on which predictions, or have how much of an impact on the prediction, and so on. The other is the white box approach, which is somewhere between the black box post hoc technique and a model based technique, where you do not use the model's structure inherently, but you do analyze some parts of the model. Maybe in a deep neural network, you try to identify layer by layer which features are important, instead of looking at the entire model as an input and as an output. So this is where you could look at things like, in convolutional networks, identifying which particular pixels led to a particular result in the outcome and things like that. Okay, so you have model based approaches, and then you have post hoc black box and white box approaches. Now, the model based approach is really simple. Let's say you've trained a decision tree. The decision tree, if you just try to visualize it, it is trained in such kind of a format. So let's say you are predicting whether somebody is going to have a heart attack based on their health information. You could have something like this, that if their age is greater than 50, then you check their BMI, and if their BMI is greater than 25, then they have the chance of having a stroke in the next 5 or 10 years. But if their BMI is less than 25, then they do not have a chance of a stroke. Okay, so this is a decision tree that has been trained on some data set, and it is interpretable by default. Now, as your models become more and more complex, the interpretability goes down. So this chart gives you a basic idea of the spectrum of interpretability versus accuracy. Now, the models that are high on interpretability, things like linear regression, decision trees, have a very limited number of features or weights or biases within them. So a very limited number of parameters, and that is why they are easy to interpret. But on the other hand, as you go to bigger models, ensemble models, or neural networks, which can have potentially millions of parameters inside them and multiple layers, then the accuracy goes up because their models are more powerful, but the interpretability of these models goes down. All right. Often, some of the more interpretable models are either linear or tree based. They have a certain very regular kind of structure, but the non interpretable models can capture complex non linear relationships and often have a long computation or training time as well. Okay. So based on this, you can decide whether you need a model based XAI or a post hoc XAI. So another way to look at classifications in XAI is by scope. Now, you could want to maybe explain for the entire data set which features are important in the predictions that the model has given you. So just looking at the entire data set. Or in many cases, you could simply talk about a single local prediction. Let's say you have an insurance application which has a bunch of health data, and then you have an AI model that says whether or not you should approve this insurance application. Now, in that case, you need to look at that particular specific prediction and identify which of the particular features led to a particular prediction. All right. And that is the two forms of XAI, dividing by scope. Finally, another way of XAI, another way of looking at explainable AI techniques is by the kind of models that they can handle. A lot of explainable AI techniques, especially the post hoc black box techniques, are model agnostic, which means they do not require knowing anything about the model. But then you also have a bunch of explainable AI techniques that are model specific. Even if they may treat the model as a black box, they may give you a better result, let's say when you're working with deep learning models or you're working with random forests. Okay, so that's another way to look at the divisions within XAI. So I hope with that you have gotten some understanding of the types of explainable AI and the different ways in which you can separate them out. So let us look at some case studies of explainable AI right now. So for this case study, we are going to look at this problem of heart stroke prediction. So let's say you have this tabular data set, and in this tabular data set, you have information about various patients, and then you have information about whether they have had a stroke or not. And what you want to do is you want to build a model, given some information about the patient, you want to build a model that can predict whether they're going to have a stroke or not. So we have information like the person's gender, age, whether they've had heart disease or not, their body mass index, their smoking status. So a bunch of information, health data, basic health data. And then here is the target column. We want to predict whether this person is going to have a stroke or not. You predict 1 if the person is going to have a stroke. You predict 0 if the person is not going to have a stroke. In this case, you can see that a large number of people in this data set are healthy and will not have a stroke, and a small number are going to have a stroke. Okay, so you may have to deal with things like data imbalance and all as well. But now, let's say you have trained some machine learning model. Let's say you've trained maybe a decision tree, maybe you've trained a random forest. How do you then interpret, or maybe you've trained a deep learning model, you have a huge data set. How do you then interpret why your model is giving a certain prediction after training? So we are going to look at 3 techniques on how you can interpret models using post hoc explainable AI methods. So the first technique that we are going to look at is called the LIME technique, which stands for Local Interpretable Model Agnostic Explainability. Okay. So as the name suggests, what it does is it zooms into a specific area. So let's say you have a specific prediction from the model. It zooms into a specific area of that model's prediction, and then it looks at other inputs around that particular prediction that you're trying to make, and it fits a linear model. So your model may be non-linear overall in the entire space of predictions, but if you really zoom into a particular example and look at the other examples around it, you can fit a small linear model to it. And then from there, you can compute feature importance using the linear model itself, right? So here's what I mean by that. I'm going to show you visually what that means. Let's say you have this feature, let's say you have this model here. Okay, so it's a complex model which creates a decision boundary between a bunch of input data points. So here you have a bunch of input data points where you're not going to predict that there is going to be a stroke. And here you have a bunch of input data points where you predict that there is going to be a stroke. Okay, so you have a bunch of data points based on a couple of features. We're not looking at all the features because we can only plot 2 dimensions on a graph. So some points indicate there's a stroke, some points indicate there is not going to be a stroke. And let's say this is the decision boundary of your model. Okay. And nonlinear models like decision trees, random forests, or neural networks can have such complex decision boundaries. Now, let's say you want to explain why the model predicts for a particular point that this person is going to have a stroke. Okay. For a particular customer, why it's predicting that it's going to have a stroke. So what you can do is you can just take a snapshot of just this area of a bunch of inputs around this particular data point. And in this area, you can see that the model has a linear decision boundary. And then you can fit a linear model over here And now after fitting that linear model, you can provide feature importance for each of the features. So you can then say, okay, this is the weight of feature 1 and this is the weight of feature 2. So if you know how linear models work, they basically say you have a certain weight multiplied by feature 1 plus a certain weight multiplied by feature 2 plus a bias, and that is the prediction of the model. So you've simplified in that small space, you've simplified your entire model to look like a linear model, and then you are predicting the importance based on that linear model. All right. So that is local, uh, that is linear or model agnostic interpretability. So that's line. All right. And the way you do this essentially is, this is sort of the loss function, or this is sort of the approximation that you do here. You don't necessarily need to understand what each part of these means. You have some pretty good libraries that can allow you to use the LIME technique to perform model interpretability. But the idea here is you take a particular complex model and you fit a simple interpretable model in the proximity of the particular data point that you are looking at, and that gives you an approximation for your main model, and then you can interpret it easily. Okay, so that is the LIME technique. Next up, we have the SHAP technique. So SHAP stands for Shapley Adaptive Explanation. Now, Shapley Adaptive Explanation is a technique that can be used locally for a particular specific prediction, or it can be averaged out over predictions, and it can be used globally to identify which features are important in the overall prediction given by the model. Okay, now unlike LIME, it does not zoom into a specific area, but it looks at the impact of each feature on the model's prediction. So once again, let's say you have a trained model for predicting whether a person is going to suffer from a heart stroke or not, given their medical data. So what SHAP is going to do is it applies a technique from game theory where it computes various feature contributions. So what it's going to do is, let's say you have 10 different input features, it's going to ignore 3 of the features, and it's going to look at the prediction that is made based on the values from the remaining 7 features, and see how far away that prediction is from the prediction when you take all 10 features. Okay, so it looks at it every time. So it does this randomization process where every time it skips a few features, and then it makes a prediction using the remaining features, and then it sees how this skipped prediction is far away from the original prediction, and then you can average it out over a bunch of different predictions to get the overall feature importance. Okay, so I'm just giving you the intuitive understanding here, and then I'll share some resources where you can dig deeper into the math, and you can also dig deeper into examples of how to use SHAP. So broadly, this is how it works. Let's say you have an input, a particular input where the age is 56, the gender is female, and then the body mass index is 30, heart disease is yes, and so on. So what it's going to do is it's going to pick a random subset of the features, and then it's going to insert a random value from the data set for each of the other features. Then it's going to feed that into the model and get a prediction. That prediction is going to be compared with the prediction that was obtained by putting in all the features, and that difference is going to be computed. And this is going to be repeated many, many times over a bunch of different predictions. And then the feature-wise differences are going to get averaged out. Okay. So eventually what this gives you is that based on this process of picking subsets and putting in random data for the features not picked in the subset, and then looking at the differences, you are going to see that what is the impact of each of the features on the final output, both at a local level, and you can average these out at a global level. So for example, here there is a prediction of 0.4, and the prediction of 0.4 comes, the impact of each feature is such that a BMI adds 0.1 and BP adds 0.1, sex adds 0.3, sex subtracts 0.3, whereas age adds 0.4. Okay, so that is how Shapley can give you a feature by feature explanation into why you're getting a particular result. Again, there's a way in which you can just import a library and then give it a set of inputs and outputs, and all the Shapley values are going to get computed. But I want you to take away the intuition here, which is that we are going to look at a subset of features and then apply those and pick random values for the other features. Then look at the difference. So that is the Shapley method, or the SHAP method. The third technique that I want to talk about is the partial dependence plot. Now, sometimes you may want to study how the target variable varies as a particular feature varies over the entire possible spectrum. For example, you may want to simply study for the entire model or for the entire data set, what is the dependence of the prediction of the model on the age, as the age varies from maybe 10, 15 to 65, 70. How does the model's target prediction change? That is what you use a partial dependence plot for. So the key idea here is this computes variation with feature. And the way it does that is by varying a feature from 0 to infinity. So what you do is you've trained a model already, and the model given an input is going to come up with a prediction. So what you do is you take your training data set, and in your training data set, let's say, yeah, so let's look at that here. So in your training data set, you have the age column. What you do is you put 0 for the age column entirely. So you replace 0 in the entire training or testing data set for the age column. Then you make predictions for the value 0, and then you take the average of all the predictions, and that gives you a certain average. What is the average prediction for this data set from your trained model for the age 0? Okay, then you change the age to 1, and then you make the predictions again, and then you average the predictions. Then you make the then you change the age to 2, and then you make predictions again and again and again. So at every age, keeping everything else constant, you just vary the age from 0 to infinity or 0 to 50, let's say, and you make predictions on this training or test set, and then you take the average of those predictions and maybe also look at the standard deviation. Okay, so it varies a feature from 0 to infinity, and then it plots the standard average and standard deviation of the predictions, and that is why it's called a partial dependency plot. That how does the target value depend on the variation of a particular feature while keeping everything else constant. Okay, so there's one key thing to remember partial dependency plot, that this assumes feature independence. If features are dependent on each other, then varying a particular feature from 0 to infinity may not make sense. But here is essentially what a partial dependency plot looks like on a particular model prediction. So let's say we are looking at the prediction of a particular model. It could be a neural network, it could be a random forest. All we do is, here we're looking at this particular column called glucose, is first in the entire data set, we set the glucose value to 0, and then we pass the data through the model. And as we pass the data through the model, we get some predictions, we average out those predictions. Then we slowly start increasing the glucose value. And as we increase the glucose value and make predictions for the entire data set, we're going to track the average here. So you can see here that as the glucose value increases, maybe up to the point 150, up to the point where glucose value reaches 150, the average prediction is generally negative. Okay, whereas once the glucose value crosses 150, the average prediction tends to become positive. So that means now you can understand that maybe under 150, maybe a glucose level is actually healthy, somewhere in between. But whereas once you cross 150, the glucose levels become unhealthy. No matter which model you're doing this with, all you need is the inputs and the predictions, and then you simply vary the glucose feature. Now, apart from the average, we have also plotted the standard deviation here. So this is one standard deviation before, and this is one standard deviation after. So this can give you the amount of variability based on the value of the glucose feature. So you can say here with a fairly good confidence that if the glucose value is about 200, then I don't even need to make a prediction. I can simply tell with a very high degree of confidence that this person is going to have a stroke at some point in the near future. Whereas over here, you might need to actually make a prediction because the standard deviation crosses over into negative and positive. Okay, so that is what a partial dependency plot looks like. So those are the three techniques that I just talked about. And this was just a quick insight into three techniques. There are dozens more, and there are dozens of libraries that you can use to implement these techniques, no matter which kind of machine learning model you're training. So I want to share a few references with you that you can check out. Now, the first one is the Interpretable ML book. So there is this book called we'll share these resources in the chat. Let me drop that in the chat right now. In fact, let's see. Yeah, so the first is the Interpretable ML book. So most of the examples that we picked out in this session come from this particular book. And you can see here, it talks about the different kinds of interpretability that you have. It has a bunch of different data sets. So it first looks at a bunch of interpretable models, then it looks at maybe some model agnostic methods, and it looks at partial dependency plots, it looks at Lime, it looks at, I believe it looks at Shapley as well. So you have a bunch of different techniques described in a lot of detail. So you can check that out. The second one that I would point you to is this collection of explainable AI resources. So this is a GitHub repository called Awesome Machine Learning Interpretability. And here you can find all kinds of tutorials, all kinds of libraries. There is this big chart showing the different ways, depending on the kind of use case you have, which kind of explainable AI technique you need to have. It's an active area of research, but there's a lot of research done already. So you can check out here a bunch of examples, a bunch of tutorials, a bunch of libraries. There's almost everything you need related to explainable AI is going to be covered here. So this would be a good place to start when you want to start implementing it. Then I want to share with you a tutorial, a series of tutorials. So this is on this YouTube channel called Deep Finder, where you have both the theory of explainable AI, specifically these 3 or 4 techniques that we're talking about, and you also have coding examples. So I encourage you to check out this particular playlist. It would be about a couple of hours long, not too long. So just check out this playlist here. You can see here, it talks about explainable AI models that are interpretable by default. It looks at maybe the Lime technique, the Shapley technique, and a bunch of different techniques. So you have both code examples here. So you can see here that there are examples of how to use the code, and there is a pretty good explanation of some of the theory here as well. So this is the place that I would go to if I want to understand explainable AI maybe in 2 or 3 hours and follow along with the tutorial. And then the final thing that I will point you to is an interpretable machine learning Kaggle tutorial. So this is a tutorial built on top of this very dataset that we're talking about right now. So this is by a notebook by Parul Pandey, and she is, I believe she's using the, she's using a bunch of data sets here, but she's explaining a bunch of things here. So partial dependence plots, Shapley values, Lime, and again, there are code examples here for you to look at as well, along with some explanation. So yeah, let me drop in all these resources. I've dropped them in the chat. There's a question, is this book using R? No, the book is not using R. The book is using, I believe it's using Python, but I think there are some examples in R as well. So that was a quick overview of explainable AI, and I will be happy to take a look at some questions here. If you do have questions, please post them in the chat and we'll take maybe 5 or so questions. And by the way, if you are looking to learn more about data science, machine learning, then and also maybe explainable AI, then do check out our data science bootcamp. We have a new batch of our bootcamp starting next month. So if you just head over to www.jovian.com, you can check out our bootcamp on data science. This is a 6-month program where we cover a bunch of different courses, starting from basic data science, even basic programming, to data science and machine learning. And we have one-on-one guidance and mentorship, and we are also including a 3-month internship now. So this is sort of roughly the curriculum where we talk about programming with Python, SQL and business intelligence, data analysis, visualization, statistics for data science, machine learning foundations, and you build 3 projects as well. So you build 3 real-world projects, and then there is an internship that you can get as part of this program as well. And you learn all the standard tools and techniques that you will need to use in data science and machine learning in companies around the world. So we have a new batch starting soon, and I encourage you to check it out if that is something of interest to you. Okay, so let's see if we have any questions. All right, I'm going to start from the top because there are a bunch of different techniques mentioned, the bunch of different questions that have been asked here. Let's see. Okay, any resources for making your own custom XAI model? Okay, that's a good question. So there is this interpretable interpret.ml, I believe, is a library which provides you a way to create machine learning models that have interpretability built in. So you're probably used to something like scikit-learn, and scikit-learn contains a bunch of machine learning models, linear regression, logistic regression, etc. But random forest, etc. But interpret ML is a library which contains which contains basically wrappers over all these machine learning models, and it gives you explainability by default. So here, for example, once you fit, let's say you have an explainable boosting classifier. Once you fit it, it's going to give you this nice way of just selecting a particular feature and understanding why you got a particular outcome on a particular prediction or maybe on the entire data set. Okay. So if you want to train your own interpretable models, check out interpret.ml. All right. Next question here. There's a question here. What is the difference between AI, machine learning, and deep learning? Well, AI is artificial intelligence. It's sort of a very broad umbrella under which you have many kinds of different techniques. You can have rule-based systems. You can have deep learning systems. You can have machine learning systems. You can have reinforcement learning systems. So there are many techniques that are available under artificial intelligence. AI systems are simply systems that can make decisions by looking at certain inputs in a way that might appear difficult to program in a rule-based fashion. So that's the first thing. Machine learning is when you train a model by looking at previous data to make predictions on new data. And deep learning is a specific class of machine learning models that is typically used with large data sets, images, and text. Okay, next up, explainable AI libraries for time series models. Well, I will have to get back to you on that. So how about you post that comment, come back, post that comment on the YouTube video, and I'll have to get back on that because I have not used explainable AI with time series models, but I would just check here on the awesome ML interpretability. Let's see. I would just check maybe no. Okay, there doesn't seem to be anything here, but I will get back to you about that because I've not used any. Can you please explain the difference between model agnostic and model specific? Yes. So if you look at the different types of SHAP models, so there's something called kernel SHAP, and there's like a deep SHAP and tree SHAP. So there are a bunch of different Shapley models or SHAP approximation methods. Now, the one called kernel SHAP can work with any type of model. You can use it with linear regression. You can use it with logistic regression, random forest, deep neural networks. But the one called tree SHAP is only going to work for tree-based models like decision trees, random forest, and gradient boosting. Now, the trade-off here is that for tree SHAP, with tree SHAP, you can get better feature importance or better interpretability for tree-based models, right? So model-specific techniques often look into the model a little bit, even though they may not use the entire structure of the model, or they may be developed for a particular kind of models, and they may give you a better result. But on the other hand, these kernel SHAP or these general techniques are often better when you're training a very different variety of models and you want to compare the explainability across all of those different types of models. So I hope that answers your question. Okay, next question. This is the bootcamp beginner friendly? Yes, the bootcamp is beginner friendly. So you can check out this. We start from very scratch. You don't even need to know programming, and you can even go explore the curriculum or check out the brochure, etc. I'm researching in this area, but I'm finding a common pattern in research papers and online tutorials. They don't really mention what these values actually mean in the context of the problem. How do I understand this? Okay, so see, you have to really think about which kind of model you're training. So let me just go back here. Yeah. So you have to look at the intuition behind each kind of model. So what you need to know first is when you're looking at SHAP scores, for example, you need to understand intuitively what SHAP is doing. What SHAP is doing is intuitively leaving out subsets of features and making predictions and studying how much difference they make to the final outcome. And then using that to give you the explanation for a particular feature, what these numbers actually amount to. So for example, what this explanation is saying is that, let's say for this particular model, if you pass in all zeros, you're going to get the output of 0.1. But when you pass in the BMI of 40, that leads to a plus 0.1 addition in the output. And then the blood pressure of 180 leads to another plus 0.1 prediction in the output. And then the sex female leads to a minus 0.3 prediction. And then the plus 0.4 is based on the age. So for this particular model, you can say that BMI has the effect of adding 0.1 into our prediction. So you have to understand the intuition and then use that intuition to interpret the numbers that are created by the model. And of course, the code and the library that you use, the mathematics behind it, is more to arrive at these specific numbers, because ultimately this is all backed by the specific mathematics. Okay. Next question. Okay, can I ask a question on Vice? Well, we may not have the time for that today. This is a slightly shorter event, but do post your question in the chat. In feature engineering, we can use both feature selection and feature extraction techniques. We know feature selection extraction like PCA is given more importance than. Let me just bring this here. Okay. It says we can use both feature selection and feature extraction techniques. We know that feature extraction is given more importance than feature selection. So do SHAP and total skips. SHAP skips features, then skips a few features when it explains about the dependency plot. Yeah, well, I'm not sure I understand the question here, but because you're combining a couple of techniques here, you have the SHAP and then you have the dependency plot. But maybe I'll just try to answer it in a more general sense. Um, so you use SHAP when you're trying to understand what is the contribution of each feature to a specific prediction, and you want to quantify that contribution. On the other hand, you use the partial dependency plot when you're trying to understand what happens to the target variable as you vary a particular feature, keeping everything else constant. Okay, so both of those are different in different contexts. They may be required in different ways. I can't really say that one is more appropriate or the other for a particular use case, right? So we'll need to look at the particular use case. Please help. Okay, I think we've answered the differences here. Do you have an idea of how XAI can be used in AI verification? Well, I'm not sure what you mean by that, but if you mean you want to verify whether the results of an AI make sense from a domain perspective, then yes. So for example, let's say you are predicting heart stroke, and you get the importance, or you get the predictions based on the lime model. Okay, you get the importance of each of the features based on the lime technique. You can then go talk to a domain expert, tell them that according to my model, these features were given such and such weightage. Do you feel this weightage makes sense? So then that other person can actually tell you whether that weightage, the domain expert can give you inputs on whether the weightage makes sense or not. So if that is what you mean by AI verification, then yes, explainable AI can be used for it. Okay, well, there's a question about the data science bootcamp. Well, do apply to the program. One of our academic counselors will talk to you, so we'll help you out there. Okay, I think we have answered. Yeah, where can I stay updated on different new algorithms and techniques like this? Well, come join our WhatsApp community. We also have a weekly newsletter. We are sharing something every single week, so you can go check out our newsletter as well. We'll drop a link to our newsletter in the chat too. It's newsletter.jovian.ai or jovian.com. I think should take you there. Okay. Then whenever new things come in, AI, okay, again, the same question. Okay, I'm gonna probably wrap up here because I can see that there are a bunch of questions that are coming in, but okay. Yeah, in terms of the case studies, well, I will drop all the links in the chat and we'll also include it in the video description. So you can go check out that. And the WhatsApp link is simply jovian.com/WhatsApp. Okay. We are a little short on time today, but I will see you in a future webinar, or I'll see you if you join one of our communities or check out, subscribe to our newsletters. So please be in touch. You can also go check out our YouTube channel. We are posting new videos there almost every day. So with that, we will end this session. Thank you and have a good day or good night. I'll see you next time.